Back at the farm today. The sun is not trying to kill us as hard as it usually does, so that's definitely a great positive. And we have three little things to show: one, two, three. So, what are these doodads, and why are we burning ourselves in this heat? Uh, so, the goal is to measure temperatures below the surface, below this beautiful surface right here. Because as you go below ground, the temperatures generally become constant, and you can use that to cool things down or maybe heat them up depending on what's the ambient temperature is. So we need to figure that out, like what's the temperature below there. We need to figure that out. How do you do that? Well, you need something to do that, and if you go on the market and you try to look for products that do that, you can't find one that was meeting our specific requirements. To be specific, like we wanted it to be real time, we wanted it to report to us directly 24/7 for extended periods of time, and we wanted it to be cheap. Like if you go out there and look for products that are meant to measure temperatures, especially scientific instruments, some of the cost was just insane, and none of them was specifically advertised to measure temperatures underground as well. They were like these benchtop heavy meters, and just not the product that we were actually looking for. So eventually we just go, what, like let's just give this a shot, and we start building things in house. So this was my first prototype for the problem. 10 Max 6675 boards ordered off of Amazon, soldered together by hand, a single ESP board connected. Idea is quite simple. So these Max 6675 boards use SPI communication, and what we have here is that I'm just connecting the CS and the SPI pin using this soldered modular boards. On one end I have like hard soldering, so it's hard, and on the other I sort of like this was taking too much time, so I just and used wires. Whatever, like it worked for about a few weeks on another farm, and when it got deployed here, it died in like 4 days. Why did that happen? First of all, the connections were not stable. Like when the thermocouples are connected to these little screws, and this thing is out here facing the wrath of the environment, those things move, and suddenly a bunch of your thermocouples are absent, or they're reporting temperatures like instead of things being 40 degrees Celsius, it's 800 degrees Celsius. Global warming is really serious, but it's not that serious, fortunately, right now. So like 800 degrees Celsius, 1000 degrees Celsius, so completely wrong, completely trash. So the second design, I wanted to make things robust, and I wanted to also design my first PCB. So I found this chip called LTC2983 from Analog Electronics. What this is basically 20 ADACs in one chip with a bunch of other features as well. So you can program this chip. This has some internal memory, and you can configure it for various situations. It has 20 input channels, and you can configure them as you want. Like you can write 4 bytes, and you can tell it, okay, you know what, a type K thermocouple is connected to here and there, or a type J, type T, whatever. All types of thermocouples supported, transistors supported, diodes supported, and thermistors supported, and some more custom stuff if you want. So really, really powerful chip, really nice chip. But it didn't work out well for me, at least. First mistake I did was choose the wrong connector. So this is what a thermocouple looks like, right? We got these again off the shelf parts. Got this from a seller. Thought, and the reason why we are dealing with thermocouples in the first place is because of the supposed reliability of these things. Because again, thermocouples are just two metals connected together. In type K, it's chromium aluminium for both of these ends, but different alloy mixes, so they change a few things around. So in one end has some magnesium silicon and some other magic maybe in it, and the other is nickel chromium in a specific percentage. And what happens is that when you heat or cool this end, the ratio with which the temperature, the ratio with which the voltage generated at the two ends that come out of here is directly proportional to the temperature. When I say directly proportional, for at least type K, you get a really good linearity between 0 degree to 200 degrees Celsius, but not all thermocouples behave linearly. Like the relationship can be a bit quadratic at times. But for type K thermocouple, and for the range that I was looking at, things are really, really linear, if the internet is to be believed, or the graphs out there to be believed. So all right then, you connect the thermocouples and it should work. Well, no. Well, initially the design that I thought was only going to use 10 channels, one for each of the thermocouple. The idea was to connect them in single-ended configuration. So what you can do is that you can put the positive lead into the input side and then just connect the other to the directly to the ground. That's why this middle pin does not have anything connected to it. Earlier, it had the other end of the thermocouple. And I was just using these 10 input channels. These 10 I had just left. I thought, you know what, maybe in future we'll do something else with this, but nothing worked as planned. So what are the issues when you're dealing with something with these thermocouples? Well, for one thing, these thermocouples, they simply break. So in this case, for example, all of the 1 meter thermocouples failed, like they died straight up, like what to say, both one meter and the 2 meter thermocouples saw massive failure rates. I don't know if that was because of the vendor I got it from, or whether that's just something common that happens with type K thermocouples. My assumption is that for 1 meter thermocouples at least, the wires that are the two wires that are going inside from here are not, what would you call them, they if you bend them too much, they eventually just break. You know, they are like that. So I guess 1 meter wire being twisted around a little bit too much resulted in those failures. But I don't know, man. Like, shouldn't they be a bit more robust than that? I didn't like crush them under a car or something. Like, this thing still works, and look at how many bends it has. And this is a 5 meter one. So for some reason, the 3 meter and the 3 meter to 5 meter ones were really reliable, but 1 meter, all of the 1 meter type K thermocouples failed for me. So anyways, like, that's one thing. So what are the issues with the PCB? Well, as I said, the thermocouples are really simple, but they can be really hard to work with because the fundamental basic principle relies on two dissimilar metals being in contact with each other. You cannot just go around and put any sort of metal in between the thermocouple and the instrumentation amplifier, right? Because those dissimilar metals again will then generate some voltage, and that voltage will interfere with the original reading that is being generated by the type K thermocouple. And that's what happened. So I had originally used these GST connectors. You go online, you can find type K thermocouple specific connectors. Now those things were really expensive. So I just thought, you know what, like, let's just go with this simple cheap connector and we'll see. We will figure this shit out. But what ended up happening was that even though when you connect using GST connectors, these thermocouples directly, what would happen is that, I don't know what metal this is, but because of this connection, the reading was really unstable. Like, it was completely wrong. And I couldn't figure it out. For a while I couldn't figure it out. Like, why is this happening? The thermocouple is connected. We're getting a constant voltage out, but it's not working. What ended up working was like just soldering the wires directly, the ends directly to the board, and just getting rid of the connector part entirely. The other issue was the single-ended configuration. So originally, as I said, I was going to connect things in the single-ended configuration. So one wire, the positive lead would go into the input and the ground would go to the common. The middle pin is common or ground, as you would say. But that doesn't work because the datasheet says that, hey, even if you connect it in a single-ended configuration, when the temperature goes low, you should be able to measure it. But that was not happening. What was happening is that the temperature would get stuck at the room temperature. So if you heat the thermocouple up, you will see the reading, right? But if you cool it down, if you put the thermocouple in, like, say, ice bath, a 0 degree Celsius ice bath, it wouldn't report 0 degrees Celsius. It would still keep reporting the room temperature, like 24-25 degrees Celsius. The reason that I believe that was happening is that even though when measured the temperature was going negative, but for some reason in single-ended configuration the LTC2983 just couldn't do anything with it. So what I had to do was use differential configuration, and that consumes 2 input channels per thermocouple, which means that both of these ends have to take two channels from the LTC2983. This means that I now cannot connect complete 10 thermocouples directly to the main board. Why? Because I need to at least leave some channels for the CGA reference connection, right? And generally speaking, if you look at data sheet, they would have something like one thermocouple and then one diode here to be used as a CJC for this thermocouple, and then another thermocouple and another diode or transistor or whatever to use as a CJC for that thermocouple. But the chip supports, you can use a single CJC for multiple thermocouples. So I'm using 8 thermocouples and one CJC. Not a good design. A stupid design if you were to be really pissed off about it. But yeah, not a great choice. The CJC itself is not that great. I've used like one of these resistors only, one of these 1 watt resistors, 10k resistors to form the voltage divider, and this is just a 10k thermistor attached here. Not that accurate, and because there's not enough thermal mass to keep this thing at a stable temperature, things moved around, man. Like everything worked in office, but when things were actually deployed here, the readings were just off, right? We have these lithium ion batteries, so they are forming the electrical backup, and then we have like this really some real mega garbage going on to like make the power supply work. We have 12 volts feeding in. We have one step up, right? So one step up to like actually boost the voltage, and then we have one step down to actually bring the voltage to 5 volts to actually power the board. Why do we have a step up? So that we can charge the batteries, right? And we have a step down so that we don't end up blowing up our board. In the end, I needed a lot more filtering that I did not anticipate to actually make things work. After even the soldering part, there were still instabilities, and that was basically due to ground loops that I had no idea would be this critical to this design. What I ended up doing was like connecting all of these thermocouples using directly some wire and connected them in a star configuration. All of these connections are coming in and connected to the ground through this 1 mega ohm resistor. I did not have like, so when online I found like designs where in the filter circuitry they would have like these two 1 mega ohm resistors connected to ground between the 2 input leads of a thermocouple. I did not have like 1 mega ohm resistors that many resistors lying around, and even these I bought from another departments, so that's why they are like 1 watt. That's all I had, 1 watt 4.7k resistors. They are connected across the thermocouple inputs, and then they are going into a star configuration down to that 1 mega ohm resistor down to the main ground. A 3.3 voltage regulator here, where like I'm putting all the grounds in using these soldered wires to like actually stabilize things. Still did not eliminate the ground loops, perhaps, most probably. So what happened? Well, in the office it worked. I was able to measure temperature of an ice bath reasonably accurately, and I was able to measure the temperature of a heated water as well reasonably accurately. And what I had done was do a 2-point calibration. I have another sensor here, like this is a DS18B20 digital sensor, 1-wire sensor, and this is really accurate. We actually use them in our IoT devices all over the farms, but the reason I did not want to use this is because they go bad. Like we have seen a lot of their failures in our operations. They get wet, the water eventually seeps in, and it doesn't work. Like it just ends up breaking over time. So that's why I did not want to use this, and that's why I wanted to go with Type K thermocouples. But that ended up being even worse somehow. So anyways, the filtering circuitry was added. All of this doodad was done in order to like somehow make this thing work. And because I couldn't connect all the 10 thermocouples to the main PCB, I pulled out 2 of the MAX 6675 boards and connected them here, and they are feeding back into the ESP. In the end, we get 10 readings. The ESP collects them and sends them over the Wi-Fi to a sheet, and that process works. We have few more like things like these buttons. One is for power and the other is to enter Bluetooth configuration mode. So I don't have a laptop with me. It's in the repair shop, and because I wanted to be able to configure it while not having a laptop with me, you click on one of these buttons, it goes into a Bluetooth configuration mode, and then you can send commands from your phone to like configure the send time intervals and things like that. Like you can configure you can add Wi-Fi credentials, you can do sorts of things like that. That software part works, but the original hardware doesn't work, so what's the point? So yeah, like a lot of learnings were there with this design. Should have used type case specific connectors, should have done better job at the filtering. There are guidance around like how the LTC VREF is supposed to be placed. I did not follow that, though like this chip worked solidly like throughout, no issues there. I also mixed up MISO and MOSI lines on the original PCB design, so I had to like do some I had to do a quick job of like changing those around. What else? So yeah, that's pretty much, I would say, it. The first PCB design failed miserably, and it did not work. A lot of effort went into this thing, and I learned a lot about thermocouples and in general electronics, but it did not work, man. It just did not work. A lot of pain went into this, and few more interesting things, like because these MAX 6675 and these 8 thermocouples are basically connected to two different circuitries. I had this issue where if the MAX 6675 thermocouples touch the LTC2983 thermocouples, then their readings, the LTC2983 thermocouple reading, suddenly gets pushed up to the room temperature. I do not understand that, and not actually room temperature, but there was just a lot of noise. If you measure the temperature on this, measure the voltage on these lines, there was a lot of like noise coming in from the shielding, and that's expected because when you are dealing with wires of a few meters length, you end up being in the frequency of like 50 to 60 hertz, and that thing generates voltages across these metals, and we can see that actually. We can see that. So I have like my oscilloscope here. So if we go and turn it on, like it turned off, I guess, while we were busy there. Let's see if it's turned on. Okay, it's turning on. Let's see. You see that blue line? That blue line? All of that is just noise in the air. And right now I haven't connected the ground lead of my probe. But when I did do that when this thing was running, it's no longer connected to the main power. But when this thing was connected to the main power, the noise was actually even higher somehow. I don't know why that is, but the noise was actually higher, and the readings were completely off. Especially the MAX 6675s failed completely. Their readings was like -12 and 800 degrees Celsius. So figure that out. For thermocouples, what I was facing the issue with is the CJC again. So what would happen, and what was ended up happening was the temperature that should have been in the range of 29-30 was 33. Some of the temperature was 34, the other is 32. So there was like a 5-degree error out there with each reading, and like we cannot use results like those. It doesn't make sense to do that. So a lot of effort went into this, but it failed. So where are we now? Well, this is the third design. This is this I call this centipede. This was centipede V1. I would call this centipede V0.1. This is millipede. What ended up happening was that I thought, hey, you know what, these thermocouples really hard to work with. I would need to do a lot to actually make them work. The CJC should have a lot of thermal mass around it. If you look at like premium, if you go to like Fluke and buy one of their thermocouple based measurement meter or whatever, you would find that the place where the connection happens, where the leads go in, there's a lot of thermal mass attached to it, and those kind of things need to be done in order to like properly get a reading out of these thermocouples. I have a bunch of these wires of dissimilar metals attached, and then I have ending up things with like these solder joints, which again introduces a new metal to metal contact within the circuitry that is probably messing things up. And I tried to get rid of those errors. So my assumption was that, hey, you know what, all of this thing is going to stay constant, and I can just sort of push the error away, hide the error away using some sort of linear regression model. So what I was doing is that I was doing this 2-point calibration. I would use this sensor, right, which is fairly accurate, plus minus 0.5 degrees Celsius. I want to measure in the range from 0 to 100 degrees Celsius, which is like actually wider than what we will be measuring in these underground holes. And what I would do is that I would dip it into the whatever solution I had prepared, the ice bath solution, let's say, and it would report 0 degrees Celsius, say, right? And this thermocouple would be reporting 2 degrees Celsius, and the other would be reporting minus 1.5. So these are offsets, right? And what I can do is that I can measure the temperature at 2 points, like 0 degrees Celsius or some other like 100 degrees Celsius, and I can create a linear regression model. I can figure out that linear equation that is true for each of these thermocouples, and I had hoped that within that linear regression model we would have accounted for all the errors that are being generated due to these dissimilar metals being in contact. That did not work. Did not work out that way. The readings were off, as I said. So we have a lot of noise that we can't do much about because we have like this massive high voltage line going over our head. We have to deal with that. So it's okay. What we have now is something different. This is it. This is the version that is working. As you can see, it's much smaller than whatever this was. And what we have is like not 10 but 20 of these DSP sensors. So like I decided to attack the problem in a different way. So underground what we have is a single 3-core utility wire, right, that is cut at like specified distances, and in between those cuts I have attached like 2 of these. So for each of these readings we are actually using 2 of these sensors. The idea is that if one fails, we will still get an accurate reading from the other one. So for each of these points we now had 2 of these DSP sensors connected, and all of them are covered with a bunch of like this raw rubber and Teflon tape and a bunch of epoxy, right, and then another layer of this raw rubber coating. So the idea is that should help prevent all of that water seepage and prevent these things from going bad. At least that's what I hope. We will figure this thing out, but for now like this thing is working fine, and you can see it working fine on the cheaper little Zoe oscilloscope that I got. So what is happening? So if you look at the yellow line is the data line. 1 2 3 4 5 6 7 8 9 10. So 10 of those what do you call them, like signals that you're observing, each of one of them is representing the readings from 2 of these DSB sensors. And once the system collects them, again the easy part is to like connect to the Wi-Fi and get them sent over to the Google Sheets using AppScript. And this design is working. It was the quickest to build. It was much cheaper than the custom PCB and whatnot, and so far it's been the most reliable one. Yeah, like this one is the one where I put a lot of my heart in. A lot of learnings happen, but god damn it. And this one is where there's some sort of elegance, given the fact that once this box is covered, it's like this big, and it's working. Yeah, so that's the story so far. We'll see how things move, how things go. We'll have to learn a lot more about thermocouples to actually use them in a reliable fashion, I guess. I guess that's it. I'm gonna just cover this thing up, put it up, and go back to office, I guess. That's it.